Guys, welcome yet again to my channel. Guys, today we are going to do system modeling, and that is modeling of mechanical systems. And so guys, we are going to do this question, and let me read the question first. Determine transfer function x2 s all over fs. Guys, for this system, which is a mechanical system, guys, we are trying to balance, or we are balancing our forces. And so guys, what we are going to do, we are going to draw the space diagram for M1 and also M2. And in drawing the space diagram, guys, we are going to indicate the direction of forces on M1. So therefore, guys, coming now to our space diagram, our space diagram for M1 is right here. And maybe guys, as you can see, we have various forces. The first force is the one already given here, which is F, which is its direction is downwards. That is Ft. Guys, as we push this one F downwards, you find that the D and the K1 will resist that. And so therefore they shall be in the opposite direction of F. And for K2, guys, it will be helping F, because as you can see, it has a mass that is hanging on it, and so it will be in support of F. But guys, since the direction is x1, we shall have an inertia force which is opposite of x1. And so therefore, guys, our equation, our space diagram is drawn according to that. So therefore, our space diagram is right here. Guys, these are the forces. We have Fm, due to inertia, always act opposite of the motion. Then we have the Fd, which is resisting the motion. That is the damper, is resisting the motion. And this spring is also resisting the motion. But this other spring is actually assisting in the movement of this mass. And so guys, now we balance those equations. So we shall have Fk2 plus F is equals to, this will be on one side, this on other side, as I have shown here. Then guys, we can now write them, the differential equations. We shall have Fk2, this is going to be Ft, this is Ft, equals to M1, this is A, acceleration, written as d squared x all over dt squared plus d. This is the velocity of the damper, and this is the displacement of the spring plus its constant there. From there, guys, we come and now write that into a differential equation. So this is our differential equation, guys. From there, guys, we come and convert that to, before we convert, we can actually bring these values on this other side, and they are here, guys, so that this is now our differential equation. Of course, even these ones are differential equations, but up to there is where now we write our differential equation. Guys, from there we convert this to what we call Laplace transform. Replace transform, Laplace transform for the equation. So guys, the Laplace transform for that equation is given by Fs. For the second derivative, we have s squared xs, that s represented the Laplace transform, the sign of Laplace transform. This one, we have ds xs plus k1 x1s minus all of that. From there, guys, we can now factor out, because as you can see in our figure here, we are asked to find x2 all over x all over fs. That is x2 s all over fs, which is our transfer function. And so guys, we are going now to factor out the x1 because we want to remove the x1 finally. And so as you can see, I have already factored out the x1 here. So that guys, I'm now going to replace this one after finding the other differential equation, and therefore I will remain with the x2 only. Guys, I now go to the second space diagram for M2. As you can see for M2 right here, guys, this is M2. We only have one attachment, so it's only this spring that is pulling this mass up. At the same time, since it's moving down, the inertia force for that is equal and opposite, so that we shall have Fm which with its direction upward. And so therefore guys, this is the space diagram. We have the Fk2 pointing up and Fm2 pointing up. Here guys, we don't have any force. In other words, F here is equals to 0. That is Ft is supposed to be equal to 0. And so guys, we shall have this as our equation. So we shall have Ft, which is 0, equals to Fk2 plus Fm2. We write now the differential equation. This is now going to be like this. We are going to have K2, as you can see here, K2. We have the extension x2, but since this is not fixed, we have x1. So we shall say K2, open the bracket x2 minus x1, because guys, this is the extension of that spring. It can be compression or it can be extension, plus ma, which is m2. This is m2 guys, d squared x all over dt squared. Oh, this is x2 guys, we are talking about this x2. So from there guys, we now have our to replace that with the Laplace transform. This one is the equation, the differential equation for that mass. Now guys, we go to Laplace transform for that. In doing Laplace transform guys, as you can see, we have put 0 is equals to, we change all that to Laplace transform by putting s, and this s squared. This s into bracket is Laplace, sign of Laplace transform. And finally guys, this is what we get. We factor out x2, we get that, minus x1. So this, we can bring it this other side. And so we have here guys, K2 x1 equals to that. Guys, the x1 now is going to be, this is now going to be our x1. Guys, now we come and replace our x1 in our former equation here. As you can see, we replace for x1. So when we replace for x1 here, as you can see guys, here we had x1. This was our x1. We come and now replace with our final figure that we have found there. And this is what now we get. This is x1. The whole of this guys is x1. Because guys, we are supposed to remove that x1 because we don't have it in our final answer. After that guys, we have removed. This is now what remains. We can now factor x2. And when we factor x2, even x2 will go here, and this x2 will remain there. So guys, we shall be left with that. We can now make the whole of this under the same denominator by multiplying K2 with this K2, so that it becomes squared. Now it will be under one denominator. Guys, this x2 now we come and bring this, the whole of this comes to this other side, and the fs comes to this side. And therefore guys, this is going to be our transfer function. So thank you guys for listening to me. Bye.